Okay, let's pick up where we left off. We're going to try to determine in which quadrant are the trig functions, sine, cosine, or tangent, positive or negative, but we're going to have this little kind of trick that we use to quickly determine where the positive ones are. So let me read you quadrant 1 again. We're just going to pick a point in quadrant 1. It doesn't matter where. We were calling this UV earlier. From there, we can draw the reference triangle. So we're going to put the hypotenuse on there. We'll always call that R. And then if we draw our right triangle in here, which we always drop to the horizontal, we have side lengths of U and V, but we really only care about if they're positive or negative. So I'm going to mark this horizontal side positive and this vertical side positive, which is what we would have if we're in quadrant 1. And just a note here, we should add, I think we maybe missed this on Friday, that is the angle that we're referring to. So when we talk about sine, cosine, or tangent of theta, it's always the reference angle. This, what we just drew, is called the reference triangle. So if we're in quadrant 1, let's just make a note here. Sine, cosine, and tangent of our angle theta. All we care is what's happening with the signs. Oh, I should note here, the radius is always positive. See my little note down here. The radius is always positive. Okay. So sine, which is opposite over hypotenuse, if we're standing on theta, that's a positive over a positive, which is a positive. In quadrant 1, that's true for all 3 trig functions because all parts of the triangle are positive. So we put a big capital A here for all of the trig functions. Now let's see what happens as we move to quadrant 2. This will maybe make a little bit more sense. So we're going to pick another point here. Again, put it wherever you'd like. I'll just put it right here. I'm not going to label it. I don't really care about the lengths. I care about the direction. We're going to set up our reference triangle. So that's going to get connected back to the origin. Here's our hypotenuse or radius of the circle again. We're going to drop to the horizontal always. We may go up to the horizontal, but we're never going to go to the vertical. And this time, if we're in quadrant 2, think about plotting a point in quadrant 2. This is the negative direction. So this horizontal side has a negative associated with it. This one is still positive, and the hypotenuse is always still positive. So now if we look at our trig functions, things will change a little bit here. Sine, cosine, and tangent. Let me slow down a second, give you a second to get caught up writing all that down. Let's see what these ratios look like. And again, we only care about their plus or minus signs. So sine of our angle, which is here now, theta is the reference angle, opposite over hypotenuse would be still a positive over a positive. So sine in quadrant 2 is still positive. Sorry about that. Okay, cosine of theta in quadrant 2, our adjacent side is negative now. So adjacent over hypotenuse would be negative over a positive. In quadrant 2, all angles in quadrant 2 have a negative cosine value. If we look at tangent, opposite over adjacent, that would be a positive over a negative. Also a negative result. So what we're going to write is, just to kind of be consistent all the way through, we're only going to list or make note of the ones that are positive. So in quadrant 2, let's put a big capital S for sine. Sine is the only positive trig function in quadrant 2. Okay, let me maybe add this to mine. Okay, so they're all positive in quadrant 1. Only sine is positive in quadrant 2, implying that the others are negative. Okay, let's move to quadrant 3. Pick a point, put it somewhere on your circle. That's just making sure we have the same radius length all the time. I'm going to go here. I'm going to draw my reference. I'm going to switch colors. We're going to have some overlap now. Do this. I'm going to draw my reference triangle, so I'm going straight up to the horizontal this time. And let's label our sides as positive or negative. Hypotenuse is always positive. In quadrant 3, this horizontal side would be, that's the negative direction. So is this one. We've got 2 negatives in there now. Let's set up our ratios. Okay, so sine, cosine, and tangent for quadrant 3. Pause and let you get that copied down. If you want, you can always pause this and try this part on your own. I forgot one really important thing here. The reference angle would be right here. That's the theta that we're referring to. So in terms of that angle, opposite over hypotenuse, here's my opposite side. Here's my hypotenuse, obviously. If you want, you could label that little one adjacent. Opposite over hypotenuse would be a negative over a positive, which is negative. In this case, that's the first time we've seen sine go negative. We'll compare that to the graph of sine in a little bit. Cosine, let's see, adjacent over hypotenuse, negative over a positive, also a negative. Not surprising, right? We've got 2 negative directions there. Tangent, though, watch what happens here. When you do opposite over adjacent, a negative over a negative, that result would be a positive. So in quadrant 3, only tangent is positive. Let's put a big capital T for tangent. Again, referring to the trig function that's positive in that quadrant. Now you could maybe guess in quadrant 4, look what's left. Cosine will be the one that is positive, but let's see that happen. Let's do our one last triangle here. Slash red here. Okay, so pick a point in quadrant 4. I'm going to go just right here. I'm going to draw my reference triangle. So I'm connecting to the origin first, and then I'm always going to the horizontal. So this one I'm going straight up here. Let's look at those red pieces. This blue one, well, I guess it's still positive, right? That is technically from the other triangle, but that's still the same direction. So we've got a positive side, we've got a positive hypotenuse, we have a negative vertical side now. Let's throw theta in there. Think about what's opposite, adjacent, and hypotenuse. And let's look at sine, cosine, and tangent in quadrant 4. Now, can I mention, we're hoping to do this one time only. We do not have to think about this every time. We're putting in the work so that we can sort of just make a broad statement about what is positive and negative where. So in this one, we've got sine, let's see, opposite over hypotenuse, we have a negative over a positive, which results in a negative. Cosine, adjacent over hypotenuse, that result is positive. And tangent would be when we have an opposite over adjacent and negative over a positive, that would always give us a positive, excuse me, a negative ratio. So in quadrant 4, only cosine is positive. Let's put a big capital C here for cosine. Now, look at your paper or look at my board. That's a lot of stuff. We went through and sort of thought about every scenario. What we're going to take from that is just this. ASTC. In those quadrants, this, and also, so the axes we're also going to think about as a plus sign. So ASTC tells us which trig function is positive in each quadrant. Okay, so if we were working with an angle in quadrant 3, and it said find tangent of that angle, we would automatically know that, oh, that one's going to be positive. If we were asked to find sine of that angle, it would have to be negative based on ASTC. You can come up with your own little phrase, but sometimes we use this. All students take calculus, ASTC. Nice little trick to help us remember that, ASTC. Okay, we'll pause there, and then we'll work through some examples in a minute. We're going to try just two examples. One where we have the angle already given to us, and then one where we have a coordinate given to us. And in either case, we're going to sort of put them on a coordinate plane, draw whatever diagram that we need, and evaluate a trig function. So take a second, pause this video if you need to. Go ahead and copy down example 1. Get that in your notes and then we'll do it together. So we're going to draw a 147-degree angle in standard position, always in standard position. Mark the reference angle and find its measure. And then, here's the new piece, let's find cosine of both the reference angle and cosine of 147 degrees. And there's some little observation to make there. So let me go ahead and sketch 147. This is theta. Our reference angle would just be 33 degrees. Check your arrows on that, your arc directions. Is that all working out okay? Now, this part, if we have the angle measure, and it's not any particularly special angle, like 30 or 45 or 90, we're just going to go right to the calculator, making sure we're in degree mode. I'm going to plug in cosine of 33 first. Again, that's right into the calculator. It's approximately, what did we get here, 0.8386. 0.8386. If we were looking on the graph of sine at 33 degrees, we would be up here at 0.8386, just to start making those connections there. So I'm going to erase that. I'll highlight it. Now, if you plug in cosine of 147, again, this is just directly into the calculator, we get approximately negative 0.8386. Why do you think that is? Notice, same number but different signs. Here's why that is. Let's link this back to this ASTC. All students take calculus. ASTC tells us that in quadrant 2, which is where we are, only sine is positive. Therefore, implying that cosine must be negative. But why wasn't cosine of 33 negative? It's over here in quadrant 2, right? But 33 degrees in standard position would be here, which, according to ASTC, then, okay, it should be positive. So we're going to use those reference angles in conjunction with ASTC to determine sine and cosine of other angles that we'll need. Example 2. I'm going to do a bunch of these variations of these together tomorrow. Go ahead and get that copy down and then come back when you're ready. This one says the terminal side of angle theta, in standard position, of course, contains the point 8, negative 5. We're going to sketch the angle and actually not only the reference angle but the reference triangle to try to determine sine and cosine of theta. So here's what we know. We have the point 8, negative 5. Let's plot that. So 8, this is 8 over here, and then I'm going down 5. That would put me right about here. But it says the terminal side of an angle contains that point. That basically means do this. Connect it back to the origin. Now, if we're going to find sine, cosine, tangent of the angle, which, by the way, the angle would be this angle, this being our reference angle, we can use the reference angle inside the triangle. We just saw in the last example, and the difference between them would be a change in sign. But if we're careful about our diagram, honestly, that will sort of take care of it for us. We don't have to make too many adjustments. What I do need to do is draw my reference triangle, always to the horizontal, and then I'm going to throw some labels on here. Think about plotting this point. If you plotted the point 8, negative 5, you would start at the origin. You would go to the right 8 units, and you would go down 5 units. I'm going to put negative on there already. I know in just a standard right triangle context, it doesn't make sense to have a negative side length. But we know we could get a negative sine or cosine value. Here's where it comes from, that negative side length. Now, sine and cosine, thinking of SOHCAHTOA, require us to find the hypotenuse as well. Remember how to do that? Use the little Pythagorean theorem. Be careful with your negatives here. If you want, you can really just leave them off. We know those negatives are all going to get wiped out when we square it. But if I write this properly, I'm looking at something like 8 squared plus negative 5 squared equals c squared, or 64 plus 25 equals c squared. So c is equal to plus or minus the square root of 89. However, we've mentioned this already, the hypotenuse is always positive. So we're going to choose positive square root of 89. Now from here, let's just use SOHCAHTOA to find sine and cosine of theta. Now theta is not in the triangle, but the reference angle is. So we're really thinking of, okay, let's stand in the reference angle. We can label our sides if you'd like. This negative 5 would be the opposite side. 8 would be the adjacent. Square root of 89 would be the hypotenuse. So sine would look like opposite over hypotenuse is negative 5 over the square root of 89. Technically that's fine, but it's not really simplified. You remember how to rationalize? We're going to multiply this by root 89 over root 89. So we get that square root out of the denominator. So technically we want this, right? 5 times the square root of 89 over 89. We could reduce it if we wanted. If you put that in your calculator, it's about negative 0.5299. Oops, that's negative there. 0.5299. And just think about ASTC for a second. So just sort of we didn't really need to use it because we were thoughtful and careful about our diagram already. But let's say we did. We just threw the lengths on there. We could say, okay, we're down in quadrant 3, only cosine is positive. So that should just sort of confirm we're on the right track here. Sine should, of course, then be negative. Cosine, very similar, but watch what happens here with the plus or minus signs. Now we just have 8 over the square root of 89, or 8 times the square root of 89 over 89. Reduce it if you can, but you can't with that particular one. But we could get a decimal approximation, again, just to kind of, let's go back and think about what the function, the graph looks like, that curve. About 0.8479 if we were to graph this. And what we don't know is what is the angle exactly, but we do know we would have a y value. You know, if our maximum here is 1, oops, that's sine, not cosine. That looks like this. We're somewhere here, 0.8479. So we can think about, what might that angle measure be? That's something we can find out in the future as well. Okay, we'll leave it there for today. We'll do a bunch of different examples like this tomorrow. Tomorrow will be a practice day. Thanks, everybody.